Hello boys and girls and everybody else. So welcome again to another science video lesson, and in this video lesson we will going to talk about a certain part, all right, a certain object that helps us in our daily lives. All right, so this particular object can be seen in a washing machine, in an electric mixer, in a electric shaver, in an electric car. Even in an electric car there's a certain mechanism that uses this particular object. And also one of the most familiar object during summer, which is the electric fan, which uses this certain part which makes your electric fan work. All right, so with that, let's try to think of it. What are common to these objects? All right, what are the common thing that we can find on these objects that we will going to talk about in our discussion in this particular video for today. All right, so with that, let's start our discussion about this particular object in our science video lesson. All right. So we are now in this discussion of our topic for today, and we will going to deal more about electricity and magnetism. So in this discussion, we will going to talk about the electric motors. So those objects that I gave, all right, as an example, are objects that uses an electric motor. So what is this electric motor? So but before we go to the mechanism and the purpose of electric motor, so let's talk about first the basic ideas on how this electric motor works. So the first one, we were going to talk about the basic ideas about magnetic field and magnetic forces. All right, what are these? The second one is the magnetic field in a current carrying wire. So we will going to talk about that one. What is this certain concept behind this functioning of your electric motor? The third one is very important. This is the magnetic force on a current carrying wire. All right? And finally, we will now consolidate those two ideas, the magnetic field in current carrying wire and the magnetic force on a current carrying wire, to better understand how electric motor works. All right, so let's start on our first topic, which is the magnetic field and magnetic forces. Let's go on that. All right, so before we go to the next part, we will have a certain question. All right, at the end of this lesson or at the end of this particular discussion, you should be able to answer how does an electric motor works. All right, so you should be able to answer how does an electric motor work, and all right, identify the parts of an electric motor, analyze how an electric motor works, and finally, I hope and I hope and I am confident enough that at the end of the lesson, you should be able to explain how an electric motor operates. All right. So, starting from the basic concept of the electric motor uses magnets. All right. It uses magnet, and these magnets create these magnetic field lines. All right. These magnetic field lines are originating from the magnet on the picture. All right. So, a typical magnet has this north and south pole, right? A typical magnet has this north and south pole, and this north and south poles is where your magnetic field came from. All right. Now, if you place a compass near this magnet that you have right here, this compass will be able to tell you the direction of the magnetic field around this magnet. And also, the compass the compass also, whenever you place the compass in this particular magnet that you have right here, will tell you and it will tell you any point around this magnet where is the direction of the magnetic field. Okay? So the direction of the magnetic field indicated by our compass here is from north to south. Alright? So the magnetic field originates from the North Pole and end in the South Pole. That's the usual magnetic field direction that we always have in a certain magnet. And what we have right here is the magnetic field is strong where the field lines are dense, and it is weak where the lines are sparse. Now, to better visualize this one, let's use this PET simulation. Okay. Alright, so on this simulation, we will try to find out if that particular statement is true. Okay, so the field lines, alright, so the field lines are, alright, so the field lines are very dense near the poles that we have right here. So, according to the statement, where the field lines are dense, the magnetic field strength is greater on that area. So let's put this magnetic field meter on that particular area, and let's record that particular data that you have right here. Alright, so as you can see here, the magnetic field there is 84.01 Gauss. Alright, so Gauss is the SI unit. Alright, sometimes it's Tesla. Alright, so 84.01 Gauss. So on the South Pole also has 61.43. Alright? So 61.43 Gauss. Alright. So meaning to say this is the value of the magnetic field near the pole. So when we put this magnetic field meter away from the poles, so somewhere over here, alright, so it tells us that the magnetic field on this area is very small. Alright, the strength of the magnetic field here on this area is very small, so at around 0.17 Gauss. And on this area, we have 0.11 Gauss. So it tells us that whenever the magnetic field lines are sparse or are dense, like the one that you have right here near the poles, the magnetic field strength is strong. Where the magnetic field lines are sparse, the magnetic field is weak. Okay? So that's the basic idea about determining the strength of the magnetic field in a certain magnet that we have right here. Alright, so let's go back to the main display. Alright, so that is the magnetic field lines. And, okay, and whenever the magnets encounter another magnet, okay, whenever a magnet encounters another magnet, so in this situation, we have two different poles, the north and south respectively. The magnetic field lines used to look like this, right? So the magnetic field lines used to look like this. So the idea was, it lives on the north pole and enters the south pole. So therefore, if you see something, or if you see the magnetic field interaction looks like this, it is the two magnets are attracting each other. Alright, the two magnets are attracting each other. And if it does the otherwise, alright, if you have two similar poles, then the two magnets are repelling each other. This is how the magnetic field lines of two north poles interacting with each other looks like. Alright, so it looks like the one that you have here on the picture. Now, if you want to see the south pole, it will be on the opposite direction. The field lines are in the opposite direction, but the same pattern that we have right here. Alright, so only the arrowhead is different. Okay, so attraction and repulsion. Alright, so what is this magnetic attraction and repulsion? These are magnetic force. Alright, these are magnetic force. So, if two poles, alright, if two same poles are interacting with each other between these two magnets, then therefore, these two poles will likely to repel each other. So, the other magnet will push the other magnet as a form of interaction. Then the other magnet will move as a consequence of that magnetic force. Alright, that is repulsion. Okay, when you have another magnet and it interacts with another magnet with different poles, alright, so they will likely to attract each other. So therefore, in this case, instead of pushing, the other magnet is pulling this magnet is pulling the magnet that is hanging over here towards this magnet. Okay? So the pulling motion, alright, so the pulling motion is the consequence, alright, is the consequence of this magnetic force that we have right here called attraction. Okay? So there are two magnetic forces that we have right here, attraction and repulsion respectively. All right. So, on this particular part, we will now dive deeper on what is this magnetism all about. Okay. So, in 1819, there was a Danish physicist called Hans Christian Ørsted. All right, and he wants to know on his experiment whether the electricity and magnetism are related to each other. Okay? He wants to know if electricity and magnetism is related to each other. So, in this case, he created, all right, this particular setup. Okay? The wire is at the center and the compass is placed around the wire. Okay. Now, the plan is he will put current on the wire and his hypothesis was the compass should respond. Alright, if there is a magnetic field around this wire, the compass should respond. Because the compass is very sensitive to magnetic field. Alright, it follows the magnetic field of the earth. So there's no reason that if this wire creates its own magnetic field, the compass will follow. Alright, so on his experiment, he found out that moving charges creates magnetism. Right? Moving charges creates magnetism. So what is this moving charges that he is talking about? This moving charges is the current. Alright, this is the current. So as long that there is a current on your wire, the wire itself will produce its own magnetic field. That is why this compass that you have around this wire is responding to that magnetic field that is produced by the current inside. Okay? Now, otherwise, if you reverse the direction of the current, the compass will respond in reverse as well. So, in short, the magnetic field is dependent on the direction of the current inside the wire. Alright, so basically, what he concluded here on this experiment is that magnetism is created by these moving charges. Alright, so we have now the magnetic field in a current carrying wire. Alright? So what is this magnetic field around the current carrying wire? Okay, and how does it work? Okay. Now, the magnetic field lines are concentric circle around the current carrying wire. So what is this concentric circle? Concentric circles are circles with the same center and it has different radius. All right? So the one at the center of the circle or the one at the center or near the center has a smaller radius compared to the one far away from the center. So that is the concentric circles. And according to Ørsted, that these concentric circles are found in the around the wire. Okay, whenever the magnetic field is produced around the wire. And the direction of the field depends on the direction of the current of the wire. Okay, so the one that you have over here. So how do we know? All right, so how do we know the direction of the magnetic field around the current carrying wire? All right, so we will use the first right-hand rule. Okay, in order for us to find out the direction of this magnetic field around the current carrying wire. Not only the magnetic field, but also the current itself. Okay, you can identify the direction of the current inside the wire using this first right-hand rule. So how does it work? Alright, so the first right-hand rule, works like this. So first you will need to use your right hand and a ball pen that simulates as a wire. Alright, so suppose the current inside the wire is going upward. Alright, so the wire or the current inside the wire is going upward. So what is the direction of its magnetic field? Alright, so in order to find out the direction of the magnetic field, you will use your right hand. So, what are the following representations here? Number one, alright, this is the current. Alright, so this is the direction of the current. The thumb represents the direction of the current. And the fingers represents the direction of the magnetic field. Alright, so the fingers are the direction of the magnetic field. Okay, so with that, okay, let's go back to your wire. If the current on the wire is going up, all right, if the current in this wire is going up, so therefore, your current The direction of the current is represented by the thumb, and you wrap around your fingers on this wire. And then in the top view, you will see that the fingers are going to a counterclockwise direction. Alright? It is going to a counterclockwise direction. So the magnetic field around this wire, if the current is going up, is counterclockwise. More so, in reverse, alright, so in reverse, we have the magnetic field moving clockwise. Alright, if the current is moving on going on this direction, so downward. Alright, so the magnetic field is going going clockwise. Alright, so that is the first right hand rule. So let me repeat. So we have the thumb as the direction of force. Direction of current, and the four fingers represents the direction of magnetic field. Alright, so that is the first right hand rule. Right. Next one. Okay, so the strength of the magnetic field near the wire depends on two factors. Alright, it depends on the following factors that we have right here. So the first factor is the strength of the wire is directly proportional to the strength of the magnetic field. So, meaning to say, as you increase the current inside the wire, alright, so as you increase the current inside the wire, it doubles, alright, it doubles the strength of the magnetic field. Alright, so if you double the strength of the current inside the wire, it doubles the strength also of the magnetic field. So that is why they are directly proportional. Alright, so the second one is the field strength is inversely proportional to the distance of the wire. So remember the shape of the magnetic field around your wire is in a form of a concentric circle. So it means that if the radius, alright, if the radius of that concentric circles is small, then the magnetic field strength is greater. Okay, or vice versa. Okay? So that is why the field strength is inversely proportional to the distance from the wire. So more so, if we put this one, alright, if we put this one into a certain formula, so we have magnetic field is represented by beta or B, and we have mu O, which is the permeability of free space. So what is this permeability of free space? This is the property of the object to accommodate such fields, like the one that we have right here called magnetic field. Alright, so that is the permeability of free space. That is a constant. Alright, so the other one is current. So as we can say here, strength of the current is directly proportional to the magnetic field and inversely proportional to radius. So this is the formula for these factors that we have right here. So this is the interaction between the current, the radius, and the magnetic field strength that we have. This is the relationship. Okay? On this formula, you will see that particular relationship. Okay? So this formula is is also known as the Ampere's law. Alright? This is part of the Ampere's law. Okay? And this formula is also the constituent of the electromagnetic spectrum. Alright? This is the formula that constituent the electromagnetic spectrum, or to be exact, the electromagnetic waves. Alright? So that particular formula. Okay. So so let's go back again to the right hand rule. Let's have more examples of the right hand rule. Okay. Okay, so in the right hand rule, we will use here certain directions. Okay, so suppose you have an arrow over here. All right, suppose that you have an arrow. Okay, now if the arrow is going towards you, okay, what does this part looks like? Okay, so if this arrow is going towards you, this part looks like a dot. Okay, so this is that part. Okay, the arrowhead. Alright, meanwhile, the arrow tail looks like, okay, when the arrow is going away from you, alright, when the arrow is moving away from you, it looks like this. Alright. So, we are dealing with three-dimensional, we are dealing with two-dimensional figures here, huh? Alright. So, The arrow tail looks like this, and the arrowhead looks like this dot over here. All right. So, suppose you have a wire, all right, viewed on this direction. All right. So you have a wire viewed on this direction, and it has a magnetic field around it. All right. So like the one that I have right here, it has a magnetic field around it. Now, if the current, all right, if the current inside the wire is moving on this direction, okay, if the current inside the wire is moving in that direction, what is the direction of the magnetic field around it? Alright, so by using the first right-hand rule, you will be able to know what is the direction of the magnetic field. So, the current, so it is, the dot over there tells you, alright, so the dot over there tells you that it is moving away from the screen. Away from the screen. Okay, and the x tells us that the direction of the direction of that indicated variable that you have right here is moving into the screen. All right. So, what is the direction of the magnetic field in that particular example that we have right there? You can pause the video and try to figure out the answer using the first right-hand rule. Okay, so it says that the current is going away from the screen. All right, so it's going towards me. The thumb is pointing towards me, and as I look upon the fingers that I have right here, as I look upon these fingers, it is going to the counterclockwise direction. All right, so it's going to the counterclockwise direction. So therefore, the magnetic field that you have right here is going counterclockwise. All right, so it's going counterclockwise. So what about, okay, so what about this one? Okay, if the wire is running vertically, okay, if the wire is running vertically and you have magnetic field around it, okay, so we have X and we have that on the other side. Okay, the question here is, what is the direction of current? What is the direction of current inside this wire? Okay, again, there's no way to answer this one, okay, without the use of your first right-hand rule. So, use your four fingers. The tip of the finger represents the dot that you have on the diagram. Alright, so the tip of the finger represents the dot on the diagram, and if you wrap around that finger, alright, so if you wrap around that finger this way, okay, it should point towards you. And then wrap around it, and the current should move downward. Alright, so the current should move downward if you do the same, if you follow my direction. Alright, so it points towards you and it moves down. So the current here is going, moving downward. Right. So another example, what about if the wire is in horizontal position? Okay. If the wire is in horizontal position, what is the magnetic field? So suppose the magnetic field looks like this. Okay, so the magnetic field looks like this. Okay, so what is the direction of the current inside your wire? Again, you can answer that question using the first right-hand rule. So how does it work? So, the fingertips are the dots that you have right here. These are your fingertips. So you put it that way, and already you can tell that the current is moving on the left side. All right, towards going to the left. The current is going to the left. So the fingers is pointing towards you. Right? So the fingers is pointing towards you. Okay? And the answer to this question that we have right here, what is the direction of the current? It is going to this direction. So to the left. Okay? So that is the first right-hand rule in action. Okay. So let's move on. Okay, so as I've said earlier, that the compass is the one that is the device that can detect your magnetic field. So basically, your compass tells the direction of your magnetic field. All right. So the compass or the arrowhead of your magnetic field represents the north, and the arrow tail of your compass or of your magnetic field rather represents the south. Okay? And on the compass, the red part is the north and the white part is the south. Okay? So that is the compass and the magnetic field. All right. So next one. Now, how can you strengthen the magnetic field around a single wire? All right? There are two techniques. All right? There are two techniques in order to strengthen the field around a single wire. Number one is bundling. All right? So you get one wire and you get another wire and you get another wire. By forming a bundle of wires, you will strengthen the magnetic field. So in this case, I have 3 wires. So the magnetic field strength here is 3 times. Alright, so the magnetic field here is 3 times. But, if you are going to use, if you are going to use a single wire, how will you strengthen, how will you strengthen the magnetic field around that single wire without adding additional wire? Alright, so you can pause this video to answer that question. So how can you strengthen the magnetic field around the single wire without adding another wire? Alright, so the answer is, that's the second technique called looping the wire or making it into a coil. Alright, if you transform this wire into a coil, the field now will be concentrated at the center. The field now will be concentrated at the center, so therefore, without adding additional wire, you can now strengthen your magnetic field respectively. Alright, so what do you call that particular wire? We called it solenoid. Alright, most of the electric motors that are made today contain solenoid inside its mechanism. Alright? That is very important. This solenoid is very important in the makings of your electric motor. So what does it look like? It looks like this. Now, this solenoid that you have right here has a concentrated magnetic field. And aside from that, it uses only one wire. Alright? It uses only one wire on that on this particular solenoid. Alright? We didn't add another wire in the process. So we strengthen the magnetic field without the additional of another wire. Okay. Okay, this is what the magnetic field looks like if the coil, if the wire is formed into a coil like the one that you have right here. This is the magnetic field looks like on a permanent magnet. And this is what it looks like in a solenoid. Now, what is the advantage of these two? Okay, what is the advantage of this permanent magnet over these two that you have over here? Okay, now this wire over here, this one, and the solenoid at the bottom, alright, they can only have magnetic field if they have current. Alright, they can have only a magnetic field if they have current. But the magnetic field doesn't need a current in order for it to create its own magnetic field. It has its own magnetic field emanating around it. Alright, so that is your permanent magnet and the solenoid and the coil respectively. Alright, so let's go now to the next part. So the next part, now what if you have two wires? What if you have two wires? Okay? If you have two wires with current on it, so we already know that current creates magnetism. So it will produce its own magnetic field. So what will happen if you have two wires? So therefore, if you have two wires, these two wires now will interact with each other and will create this magnetic force. Alright? So remember, forces works in pairs. Alright? A single magnetic field doesn't have any force. Alright? A single magnetic field doesn't have any force at all. But if you place that magnetic field near another magnetic field, that's the time that it will create a magnetic force. So the forces that you have right there is either attractive or repulsive. Okay? Now, it depends on the direction of the current in both wires. Okay? It depends. So, now if the current is moving at the same direction, All right? If the current is moving in the same direction, then therefore, the two wires are attracted to each other. Okay. Meanwhile, if the current is moving in the opposite direction, the two wires is likely to repel each other. All right? So, take note of the direction of the current that you have right here in attraction and the repulsion of two wires. So, remember, you must have a two magnetic field in order to achieve these two forces that you have right here. Otherwise, if you just have one magnetic field, then therefore there will be no forces that will interact between those two wires. All right. So that is the magnetic field. Okay, so this is the discussion about the magnetic field around the current carrying wire. All right. So let's go now to the next. All right. Let's go now. On the next video, you will okay, on this next video you will see, or next part of this video, you will see now the magnetic force, all right, around the current carrying wire. Since we are talking about this one, the magnetic forces, what will be the effect of this another magnetic field to this current carrying wire that we talked about earlier? All right. So that's it for this particular part of the video called magnetic field around the current carrying wire. This is the second part of our video lesson about electric motors. So, but before we go to the main topic itself, all right, so let's have this video first. Okay, so what do you think? Okay, if I pass a current through this wire, all right, so if I pass a current through this wire that you have right here, that you see right now on your screen. So if I pass a current on this wire over a magnet, over a permanent magnet at the bottom, all right, below this particular wire, what will happen to that wire? All right, you can post this video. You can post this video and put the answer in the comment section. So what will happen to this wire if I pass a current on it and below it is the permanent magnet? So what will happen to this wire? Okay, so if you say, all right, so if you say that it will move, okay, if you say that the wire will move, okay, back and forth, then you are correct. So let's play this video. All right, so on this video, you see that the wire is moving back and forth. Now the question here is how? How does it, what is the mechanism? All right, what is the explanation behind this particular motion of the wire on this video? Okay, so what is the mechanism behind that particular motion? Okay, now in this video, in this part of the video, that is what we will going to talk about. Okay, so that is, okay, so that setup that you have over there is called the electromagnetic swing. All right, that is an electromagnetic swing. That is basically a simple motor. All right, that is a simple motor. All right, so that is our discussion for today, or for this part of this video, for the part of this video. So let's jump right into it. All right, so what you have seen earlier, that is an example on how the magnetic force interacts with the current carrying conductor. All right, so instead of having one magnetic field, we have now two magnetic fields in the scene, okay, that we have over here. So what will happen? So if you have two magnetic fields on the scene, so therefore you will now have your magnetic force. All right, so how does this particular principle works? Okay. So, the magnetic force on a current carrying conductor, okay, is equal to the product of its length within the field. Yan. So, what is the length that we are talking about here? The length of the wire. Okay. And the current inside the wire is also noted here. Okay. Now, doing so, okay, what is around the wire is the external magnetic field coming from the permanent magnet that you see on the demonstration video a while ago. All right. So in short, Okay, and not also the external magnetic field, but also the position of the wire over that magnetic field. All right, or the sign of the angle between the conductor and then the magnetic field. So in short, we have this particular formula. So we have F is equal to ILB sine theta. Okay, so what does this particular formula tells us? It tells us that the force is directly proportional to the strength of the current inside the wire. All right? And not only that, but also the length of the wire is also used here. Okay? Excuse me. And also with the external magnetic field. All right? The stronger external magnetic field, the greater the force. Now, what about the sign over here? What about the sign over here? The sign over here talks about the perpendicularity, all right? The position of your wire over the magnetic field. Okay? So, if it is parallel or perpendicular. Now, if it is parallel, that is 0 degrees. Now, if you took the sign of 0 degrees, the answer will be 0. And if you took the sign of a perpendicular form of a line, which is 90, the answer is 1. Alright? So, meaning to say that the angle, alright, that the angle in which the wire is placed over the external magnetic field creates this particular force, okay? And this particular angle is where the force depends on. Alright? So, meaning to say that if the wire is placed perpendicular to the magnetic field, then therefore you will achieve a force of 1. And if the wire is placed on that magnetic field in a parallel position, then the force is 0. Right? Then the force is somehow 0. Okay, so what do we have right here? Okay, so what do we have right here? So these four things that you have right here affects the force experienced by the current carrying conductor. Okay, so this is how it looks like. Okay, so we have the magnetic field around the current carrying wire in green, and we have the permanent field in red. So once they interact with each other, the result is a certain force that will be applied on the conductor. All right, there will be a force that will be applied on the conductor. So in this particular principle, the conductor will move. Okay, the conductor will move. Now the question is, what manner of motion? It depends on what kind of position does the conductor is placed in your magnetic field. All right, so that's the interaction. Now, don't forget that the current also plays its role in the magnitude of force. The greater the current, the greater the magnitude of force. All right, so this is what we are talking about earlier, the perpendicular, the placement. All right, the placement of the wire over the magnetic field. If it is perpendicular, you will achieve magnetic force. If it is parallel, the force is always equal to 0. Okay, in that particular process. Okay. Now, all right. Now, on this particular view, on this particular slide, we will now try to find out what will be the effect if the wire is in a form of loop. What will be the effect of this magnetic field? What will be the effect of this external magnetic field on a loop wire? All right. So, suppose you have here two magnetic fields, or two magnets, all right, which is placed as north and south respectively, and the magnetic field is going to that direction, so north to south. All right. So, if I place a loop of wire at the middle, what will happen to that loop of wire? Okay, you can pause this video if you want to. So, what will happen to this loop of wire? So, suppose the current flows starting from this position, starting from this direction and ends in this direction. All right, so it goes like this and like so. Okay. All right. So the question here is, what is the force? All right. What is the direction of force on this particular area? Okay. So the question here is, what is the direction of force on that particular area? Okay. So what is the advantage of having a loop wire over here? Having a loop wire creates two-directional current. Okay. One that is going on that direction, the one that you see on this diagram, and the other one is going on a downward direction on this side of the wire, on this particular side of your wire. Okay, so instead of going in one direction, the current now goes into two direction. So what will be its effect on the force to your wire? All right, what will be the magnetic force, or what will be the direction of the magnetic force on the wire? Now, in order for us to find out the direction, we will use the second right hand rule, all right, that is provided to us to answer this question. All right, so what is the second right hand rule? Okay, so what is the second right hand rule? So again, we will use your right hand, okay, for this process. Okay, so the thumb represents the direction of force. The thumb represents the direction of force, and the middle, or the index finger, all right, so the index finger represents the direction of current. All right, this is the direction of current, and this finger, the middle finger, represents the direction of magnetic field. Okay. This is the direction of the magnetic field. Again, direction of force, direction of current, and direction of magnetic field. So as you can see, these three fingers is working in a perpendicular manner. All right, the pattern is perpendicular. Okay, so you cannot make this one parallel over the other. Okay, it should be perpendicular. Okay, so with the use of this second right hand rule, we can now answer the question on the diagram. Okay, let's go back on the diagram. Okay, so what is the direction of force on that particular side of the wire? What is the direction of the force? Okay, so we have current, which is going upward. Okay, you twist. Okay, we will going to twist our right hand to the side where the magnetic field goes. All right, so the magnetic force is going towards the screen. All right. So based on our second right hand rule, the force is going towards the screen. All right. Now, let's take a look at this particular side of wire, this side of wire that you have right here. Now, if the current over here is going to that direction, if the current over here is going to that direction, what will be the force on that wire? So remember, take a look. So the current is parallel to the magnetic field. The current is parallel to the magnetic field, which is letter I. So the current is parallel to the magnetic field. So therefore, the force there is zero. Alright, so the force there is zero. Okay, on that particular wire. Now, let's go on this side of the wire. Alright, let's go on this side of the wire. The current here is moving downward. Alright, so if you follow the pattern of the current, which started right here, okay, it goes up over here, it goes to the left on this side, and it goes downward. Now, the question is, what is the direction of force? Alright, so what is the direction of force on this side of the wire? So, we use the right hand rule. The current is going down. Then the magnetic field is going to the left, to the right. And upon looking at it, this thumb is pointing towards me. Alright, this thumb is pointing towards me. Then therefore, the magnetic force is going away from the screen. Alright, so it is going away from the screen. So that is the magnetic force on that side of the wire. Now, okay, you can pause this video if you want to after the question. Now, what will happen to the loop? Alright, so what will happen to the loop if you have two forces of two opposite direction? Okay, what will happen to your loop here if you have forces in two opposite direction? What will happen? Okay, so you can pause this video if you want to. Okay, so alright, so what will happen to this what will happen to this wire? Okay, what will happen is this wire will likely to turn. Okay? So this wire will likely to turn because you have two sides of the wire which has different direction of forces. Okay? So it will likely to turn. Okay? Just like what we have right here on this demonstration. So, okay. So in this demonstration, what you will see here is the wire which is looped the same it was looped the same way as your diagram that we have earlier. So as you can see here, if we pause this one, okay, so we have two sides of your wire. We have this side and we have this side at the bottom. Okay, so as it encounters this external magnetic field coming from this permanent magnet, as it encounters this magnetic field coming from this external magnet that you have right here, so the wire turns. Okay, the reason that this wire turns because the two sides of this wire have two different forces, two different direction of magnetic force. So, this particular wire that as you see on this demonstration will likely to turn. Okay? So, that's how it works. Okay. So, basically, that's how your electric motor works. Okay, inside your electric motor there are forces there that has two opposite direction, and by using that two opposite direction, the motor now achieves your rotational motion just like what you see here. Okay? So, that is your demonstration. Okay. Now, looking at other perspective, we have it like here. Okay. This time the force, if we view this particular diagram on this direction, okay, on this point of view, we have here the force going up and the other force is going down. Okay. Okay. So next one. Okay. So the rotation. Okay. All right. So let's practice your second right hand rule. All right. So let's practice your second right hand rule with these examples that we have over here. All right. So okay, excuse me for that. Okay. So let's start first. What are these examples? Okay. So the examples that you have right here is looking for the magnetic force. Okay. All of them are asking you to find the direction of the force respectively. Okay, so what is the direction of the magnetic force? So, in order to answer these questions, we will use the second right-hand rule. So, let's answer letter A. So, the current is going downward and the magnetic field is going out of the screen. So, this magnetic field over here is pointing towards me, right? So, the answer is the magnetic force is going to the left. All right, so the magnetic force is going to the left. So there you go. All right, so that's the magnetic force going to the left. All right, next, letter B. Okay, so the current is going up, then the magnetic field is going to this direction, to the right. Okay, so therefore, the magnetic force is going towards the screen. All right? So the magnetic force is going towards the screen, so that is the force. All right, next one, letter C. All right, so letter C. So the current is going this way. All right, so the current is going this way, and the magnetic field is going inside the screen. All right, so going inside the screen. So there you go, going inside the screen. Right. So what is the direction of the magnetic force? The magnetic force is going. All right, the magnetic force is going up. Right. So we draw an arrow here. It is going upward. That is the magnetic force. All right, next one, letter D. All right, so what is letter D? What is the magnetic force, or what is the direction of magnetic force in letter D? The answer is the force is 0. Why? Because current is parallel to the direction of the magnetic field. Okay, let's go in letter E. Okay, so the current is moving towards the screen. Okay, that's an X. It goes towards the screen, and the magnetic field is going upward. All right. So the magnetic field is going upward. There you go. The magnetic field is going upward. And what is the direction of the magnetic force? Okay, so if we follow this direction of the thumb, so the magnetic force is going to the right. All right, so the magnetic force is going to the right. Is the magnetic force. Okay, next one. All right, so next one. What is the magnetic force on letter F? All right, what is the magnetic force on letter F? So the current is going out. All right, so this one pointing towards me. Then the magnetic field is going to that direction. All right, so if we follow the thumb, if we follow this thumb, so the magnetic force is going downward. All right, the magnetic force is going downward. So we put the arrow here, and the magnetic force is going downward. All right, so that's the first set of examples. Let's go to another set. Now, in these examples, we are asked to find out what is the direction of current. You have your magnetic field, you have your force, and your magnetic field respectively. What is missing is the current. All right, so let's find out what is the direction of the current on these examples. Okay, again, you use the second right-hand rule. The second right-hand rule. So do not, just a tip guys, do not mix it with the first right-hand rule. The first right-hand rule is independent with the the second right-hand rule. Okay, so the force is going upward on the diagram, right? The force is going upward, and the magnetic field is going away from the screen. All right, so it's away from the screen. So what is the direction of the, all right, the magnetic field, rather, sorry. The magnetic field is going away from the screen. So the direction of the current is going to the left. All right, so the direction of the current is going to the left on this position. Right? So magnetic field is away from the screen, so the current is going to the left. So that is your letter I. Okay, next one. How about the letter B? So the force is going upward. Then the magnetic field is going to this direction. All right. So the magnetic field is going to this direction. So as you can see here, it's going to that direction. So therefore, the current is moving away from the screen. So it's pointing towards me. So it's going away from the screen. So that. And the last example for this part, letter C. Okay, what is the direction of the current? So the force is going that way, and the magnetic field is going to that direction towards the screen. So the magnetic field is going that way. So therefore, okay, so on this configuration of your right hand, okay, so it tells us that the current is moving upward. Right? So this is the current, that the current is moving upward. There you go. Right? So that is the current. Okay, so we are done with the second examples. So second set of examples. Now we are now on the last set of examples. Okay, now in these examples, we are asked to find out, since we have force and since we have current, we are asked to find out what is the direction of the magnetic field. Again, you can answer this one using your second right-hand rule. All right. So, what is the direction of the current? Upward. What is the direction of the force? There. So, the direction of the magnetic field is going towards the screen. All right. It is going towards the screen. So, we can put it X. Rather B. All right. So, right. Next one. How about letter B? Okay, how about letter B? The current is going down, and the force is going towards the screen. Right? So it goes towards the screen, the force, and therefore the magnetic field, this guy over here, the magnetic field is going to the left. All right. It's going to that is the magnetic field. Next one. How about letter C? The force is going upward. All right, and the current is going on this side to the left, and therefore the magnetic field is going. All right, so it's pointing towards me. It's going away from the screen. All right. So it is moving away, or the magnetic field is moving away from the screen. So these are the two examples, or these are the three examples of how you will use your second right-hand rule in order to find out the direction of force, the direction of the magnetic field, and the direction of the current. Alright, so don't forget the right-hand rule number 2. So basically, alright, so basically this is what this part is all about. This is all about the magnetic force on a current carrying conductor. Alright, so to wrap this part up, alright, to wrap this part up, whenever you have two magnetic fields interacting with each other, magnetic force in a form of attraction and repulsion will likely to be produced. Alright, will likely to be produced. And therefore, what is the consequences? Alright, what is the consequence of that to our conductor? The conductor will move. Alright, the conductor will move at any form of movement because of this interaction. Alright, so that ends up this part of the video called the magnetic force in a current carrying conductor. So hello again, boys and girls and everybody else. So this is the third part of our video lesson about electric motors. Alright, so in this particular part, we will now culminate. Alright, we will now consolidate everything that we have learned. First, on the magnetic field around the current carrying wire and the magnetic force on a current carrying wire. Alright, now before we go to that discussion, so I will show you first. Now, I will show you first the first electric motor that was created by Michael Faraday. Michael Faraday was inspired by the experiment done by Hans Christian Ørsted. Alright, so he created an experiment and eventually leading to this. So this is the first electric motor. So in this case, instead of using mercury, I used I use salt water in the replacement of mercury. So this is how his electric motor works. So as you can see here, the one at the center, alright, so the one at the center, the copper wire at the center is revolving around the magnet at the middle. Alright, so as long that there is an electric current, at the copper wire coming here, alright, so with this electric current over here, flowing to the copper wire and going to that wire, and then passing through the salt water and going back to the aluminum and then goes back again to the source. Alright, so this is the first electric motor created by Michael Faraday. So the question here is, how does this one works? Alright, so how does this one works? Okay, so in our discussion, or in this part of the video, we will going to talk about the parts of the electric motor and the mechanism on how it works. Okay, so this is the first electric motor created by Michael Faraday himself. Alright, so electric motors. Okay, so the question that we have right here is, what are the parts of the electric motor and how does it work? Okay. Alright, so electric motors convert electrical energy to mechanical energy. So basically, that's the definition of an electric motor. This is a device that that transforms electrical energy to mechanical energy. Alright, so the disc that rotates around, your motor is called the rotor. Alright, and also this disc will keep spinning as long that the external magnetic field is kept on reversing as the disc passes by. Alright, so that's the key point here, right? And also, in the motor, there is what they call, or there are what they call stationary magnets. All right? There should be a stationary magnets. And these magnets are very important in the mechanism of your electric motor. All right. Now, how to spin the magnets? All right, how to spin this disc using magnets? All right. So in this picture, okay, if you notice this magnet on this picture, all right. So the white being the south and the red being the north. All right. So as you can see, okay, as you can see, this pole that you have right here will be attracted to the north, all right, to the north pole of this part of the rotating disc. Okay? It will be attracted to that part, and therefore it will follow, or it will be pulled towards that particular magnet. Okay. Now, if you reverse the polarity of the magnet that you are holding, okay, if you reverse the polarity of the magnet that you are holding, so remember that this one is the one that is attracted on the first part. Then, if you reverse that one, it becomes the North Pole. So therefore, these two together, these two that you have right here, will be repelled. Okay, the force that is in between them will be repulsion. So therefore, it will push that particular magnet, it will push this magnet away from this magnet. Okay, as a consequence of that particular force. Okay, so as you do that, okay, as you do that motion, as you reverse this particular magnet time and time again, as you reverse that one, what will happen to the disc? The disc will do attraction and repulsion several times, then therefore it will rotate. All right, it will achieve a rotational motion. So, what do you call this particular process? This process of reversing the magnet in order to rotate the disc is called commutation. All right, so commutation is the reversing of the current in the electromagnet, changing its polarity in the at the end of the day. All right, so commutation. And the part that performs this commutation is called commutator. Alright, the part that performs the commutation is called the commutator. Alright, so, okay, it looks like this. Okay, inside the motor. Okay, so the electric current over here is different from the electric current on the second picture. Okay, once you change the direction of the electric current in the coil of wire over here, you change the polarity of your magnet respectively. Alright. Once you change the polarity of the magnet, then the disc will rotate. The disc over here will rotate. Okay? So doing so will achieve the rotational motion of your motor. Alright? Okay. Alright, so we have here the AC and DC motor. So motors that run in alternating current. So what is an alternating current? An alternating current is a form of current that goes into opposite direction. All right? These are current that goes into opposite direction. So there's a current that goes this way, and there's a current that moves on the other way. All right? So opposite direction. That's alternating current. And it was developed by Nikola Tesla himself. All right. Now, in an alternating current, there is no commutator. In an alternating current, there's no commutator because the current itself is the one that can change the polarity of your magnetic field. All right? The current itself is the commutator itself. Okay? So, that's the AC motor. While on the DC motor, it requires a commutator. Now, where can we find the commutator in the DC motor? It is located here. All right? Is located here. The number of commutator depends on the number of electromagnetic coils. Now, if we will zoom this one out, zoom in. All right. So as you can see here, you can have okay, you have 3 electromagnetic coils. So as we discussed earlier, all right, as we discussed on the first part of the video, as we discussed on that part, that the solenoid is very important inside your inside the mechanism of your motor. Okay, so this is the solenoid that we are talking about in the first part. So we have these 3 electromagnetic coils over here that are attached through the 3 commutators that we have over here. Okay, there is the shaft, that runs at the middle of this armature, and we have the iron core. All right. So when these coils are powered with electric current, it creates its own magnetic field. All right. So the coil must be the same. The number of loops on this coil must be the same on these three electromagnets. All right. Now, to complete your DC motor, it must have your permanent magnet surrounding this armature that you have. Okay? So, remember, guys, remember that forces works in pairs. So, the first magnetic field will come from this permanent magnet, and the second magnetic field will come from these coils that you have over here. All right? So, that is your DC motor. Okay, so again, the DC motor has a commutator, and the AC motor has a slip rings. Right? It doesn't require a commutator. All right? The commutator itself on your AC motor is the current itself. All right? It runs back and forth. While on the DC motor, the current runs in one direction. All right? Next one. Okay, in an electric motor, there are three key parts. If one part is missing, the electric motor is useless. All right. So, the first part that you have right there is the rotor. Okay, that's the rotating element. Okay, the second part is the stationary magnet. Okay, that surrounds the rotor, which is very important. And the last part is the commutator. Now, if this one is an AC type of motor, then therefore the commutator is not needed anymore. All right? So, these are the three parts that you have right here that makes up your motor. Okay. Next one, the rotating part of the motor, or called the armature, it has three electromagnets that you have right here, as we talked about earlier. Okay, which is surrounded by your permanent magnets on the side. Okay. Next one, the permanent magnets. The permanent magnets create this permanent external magnetic field that creates these magnetic forces inside your motor. Now, as long that the magnetic field coming from this permanent magnet interacts, right? Interacts with the magnetic field coming from this coil that you have right here. Once it interacts with the magnetic field from this coil, it will creates this rotational motion. All right, it will create this rotational motion, just like what you've seen on the part 2 of this video lesson. All right, the simple motor and the demonstration, it's basically the same thing. Okay, that's the commutator. All right, next one, the rotor spins. As the rotor spins, the three plates that you have right here, these three plates that you have, one over here, one over there, and one at the bottom. Okay, these three plates come contact with the brushes that you have right here, the positive and then the negative brush, which is connected to a power source. Okay, which is connected to a power source. And as the electric current flows through the brushes, what happens here is it turns the motor, creates this magnetic field, and turns the motor respectively. Alright, so that is the electric motor. That's how the mechanism. So, doing so, it will look like this. Alright? So, as long that this external magnetic field is present, and very important, as long that there is a source of an electric current, whatever source it is, alright, whatever source it is, it doesn't matter. As long that there is a source of an electric current, the motor will work. Alright? Remember, on the first part of this video lesson, remember that without electric current, there will be no magnetic field around the current carrying wire, which is very important. That is a very important concept. Right. So, as a summary, guys, we have the rotor, parts of the motor, we have the rotor, the fixed magnet, and the commutator. Right? And in order to end up our third part of the video lesson that we have right here, an electromagnet is needed for your electric motor. That is the basis of your electric motor. Okay? The motor runs on electricity. Alright, without electricity, the motor is useless. Okay? So the electromagnet also. Yeah. Okay. So the electric motor is all about magnets and magnetism. So motor uses magnets. Without these magnets, there will be no motion that will be created on your motor. Now, what is this motion? This is the rotational motion, and the rotational motion is achieved because it follows the certain principle of magnets that opposite attracts and like poles repel. Right? So rotational motion is achieved by doing this particular process over here. Opposite attracts, then like poles repel. Then lastly, the motor consists of two magnets. Always. It must there are some motors that are made up of several magnets, but the minimum amount, all right, the minimum amount a motor should have must be two. All right? Must be two. There is no motor that runs on one magnet only. All right? There's no such thing as a motor that runs with one magnet only. All right? So with that, this is the third part of the video lesson about the electric motor. All right. So I hope you did learn something about this three-part video lesson about electric motors. So we started with the magnetic field around the current carrying wire. The next one is the magnetic force on a current carrying wire. Combining the two together explains the mechanism of your electric motor. All right. So if you get something about this video lesson, don't forget to hit the thumbs up button, the like button on this video, and subscribe for more videos like this in the future. And don't forget to hit the bell button so that you will be notified if there is a new video like this that will be posted in the YouTube website. Alright, so don't forget, if you like this video, don't forget to comment on this video. That will help me a lot in the algorithm for this video. Alright, so let's see each other on the next video lesson. Okay, and don't forget to stay safe and be productive. So thank you guys, and let's see each other next time. 笑えない笑顔を見せた I love you もろくに言わない口下手で